All right, we all know about pushes and pulls, right? But what about the forces you can't see? The ones that work without ever, actually touching anything. Turns out they're some of the most powerful forces in the entire universe. So today, we're going to pull back that curtain and see what's really going on.
Seriously, think about it for a second. You drop a ball, what's pulling it down? There's nothing physically connected to it. Or when you take two magnets and feel them push each other away, how do they even know the other one's there? What's going on in that empty space between them?
Now, it might feel like magic, but I promise you, it's not. In physics, the answer is this incredible concept that explains everything from why we stick to the planet to how our phones get a signal. It's called a field. And it's the secret ingredient to every single force that acts at a distance.
Okay, so this idea probably isn't brand new to you. Back in middle school, you definitely talked about these non-contact forces. Let's just do a super quick refresher to get us all on the same page.
A non-contact force was, well, exactly what it sounds like. It's a push or a pull that works over a distance without anything physically touching. Like gravity keeping your feet on the ground, a magnet grabbing a paperclip, or static electricity making your hair go wild. And to explain how this all works, scientists came up with this amazing idea of a field.
Right, so that's the middle school version. Now it's time to level up our thinking to the high school standard. A field isn't just some vague area of influence. No, it's a real, actual, fundamental part of the universe.
And this, right here, is the absolute key. This is the big idea. A field isn't something that just turns on when two things get close. It is a permanent, invisible aura that an object creates just by existing. The Earth's gravitational field is filling the room you're in right now, whether you drop something or not. It's a constant, invisible reality.
So what creates these fields? Well, it all boils down to a specific property. For gravity, that property is mass. Anything, and I mean anything that has mass, from a grain of sand to our entire galaxy, creates its own gravitational field that stretches out into space.
And guess what? It's the exact same logic for electric forces. The special property here isn't mass, it's electrical charge. Any particle with a positive or negative charge creates an electric field all around it. Are you starting to see the pattern? A specific property creates a specific kind of field.
And to finish off the big three, we've got magnetic fields. These are created by magnets, of course, but also, and this is super important, by moving electric charges. So there you have it, mass, charge, and moving charge. Those are the sources for the main fields we deal with every day.
Okay, so we've established that a field is this permanent thing. But how strong is it? How can we actually measure its intensity? Let's zoom in on gravity to see how we take this idea from just a concept to something we can actually put a number on.
You have 100% seen this number before. We call it little g, and you learned it as 9.8 meters per second squared, the acceleration of any falling object here on Earth. That number describes what happens to something in the field.
But wait, there's more. That's only one side of the coin. That exact same number, g, has a totally different identity, a deeper meaning. It doesn't just describe the effect of gravity, it actually tells us the strength of the gravitational field itself.
So we can also write g like this, 9.8 newtons per kilogram. This changes everything. What this tells us is that right here, on the surface of the Earth, the gravitational field pulls on every single kilogram of stuff with a force of 9.8 newtons. This is the field's strength. It's a measure of the field's intensity, not just the acceleration it causes.
And understanding g as the field strength is the magic key to finally clearing up one of the biggest mix-ups in all of physics, the difference between mass and weight. They are absolutely not the same thing, and the field is the reason why.
Let's break this down. Your mass, that's the amount of stuff, the number of atoms you're made of, we measure it in kilograms. And it is constant. It never, ever changes, whether you're here on Earth, on the moon, or floating in deep space. Your weight, on the other hand, is the force of gravity pulling on that mass. We measure it in newtons, and it completely depends on how strong the gravitational field is where you happen to be.
So how do we tie all this together? We've got mass, we've got weight, and we've got field strength. Well, physics gives us this beautiful, simple, and incredibly powerful little equation that connects it all perfectly.
And here it is. Fg equals m times g. Or, in other words, the force of gravity, which is just another name for weight, is simply the object's mass multiplied by the local gravitational field strength. This little formula is the tool we can use to figure out the force of gravity on anything, anywhere.
What this shows us is a really simple, direct relationship. The force of gravity goes up if you increase the mass or if you increase the field strength.
If you double an object's mass, you're going to double its weight. Or, if you take that same object to a planet with a gravitational field that's twice as strong, its weight also doubles. It all comes back to that key idea. The stronger the field, the greater the force.
Let's make this real. Imagine a person with a mass of 60 kilograms. That 60 kilograms of stuff is the same everywhere. But on Earth, where G is 9.8, they weigh 588 newtons. Now let's zip over to the Moon. The field there is super weak, only 1.6, so their weight plummets to just 96 newtons. But if we took them to Jupiter, with its monster gravitational field of 24.8, they'd weigh a staggering 1,488 newtons. Same person, same mass, but a totally different field means a totally different weight.
So the big takeaway here is that fields are real. They're an invisible but totally fundamental part of the very fabric of space. They are the universe's way of letting things touch each other across vast distances. And that leads to a pretty mind-bending final thought. What other invisible fields might be out there all around us, shaping our universe in ways we haven't even begun to discover?